So now we're going to introduce another idea that comes out of some of this electrodynamic stuff that we're talking about. And it's an interesting idea about light and its ability to push on things. Now we know that light carries energy. And so since you've got energy, then it's moving energy from place to place. So you've got a laser here and sending light off, and so that means energy is moving from place to place. So if you're a detector over here and you're detecting the light, then what's happening is that you're getting energy over a period of time. Well, that's power. And so power carries energy. Well, we know energy is related to work. So power is the rate of change of energy, so the rate of change of doing work. And so we want to investigate this and what this all really means. Well, you remember from Physics 1, power, if you have a constant force, is going to be velocity times force. In fact, even if it's not constant, this is your instantaneous power at a particular moment. Well, if you imagine that you've got a charged particle of some sort and you've got changing electric and magnetic fields, then the force is going to be the Coulomb force. It's actually going to be the complete force here, the electrodynamic force. So it'll be QE plus QV cross B. So this is your electric force and this is your magnetic force. So they're both acting on something because electromagnetic waves actually carry both. And so we look at that and we say, okay, so this is great. Well, interesting thing, this is a dot product right here. This over here is a cross product, V cross B. Well, V cross B is going to be in a direction that's perpendicular to both V and B. Well, V dotted with something that's perpendicular to it is 0. So that means when you do the dot product, this term is going to go away. And so the power is going to be VQE. Okay, assuming that we're pushing it primarily in just that one direction. So that is the rate of change of energy, the rate at which you're doing work. So the rate at which you're doing work is VQE. Well, now what we want to do is talk about, okay, so we're doing work, and you look at that and say, well, okay, so you're doing work, but as light travels by, the electric field, it gets bigger and smaller, and you're moving back and forth. And so what we really want to know is not just not just this, but the RMS average of the work being done. And so so what I can do is I can talk about the RMS average of that. So this is going to be like the average. So the RMS average. Well, we know that the Q doesn't change, so it's just the RMS average of VE. All right. So now we've got an idea here, and so sorry, that's not. It's going to be VE right there. Okay. So let's think about the force itself, because we got the force, and the force keeps changing too. So the force is going to be QE plus QV cross B. Okay. If we want to find the actual average force, so the average force, well, the average of force, the average of that's going to actually be 0. So the average force is going to be the average QVB. Okay. Well, the Q comes out, so Q average of VB. Okay. Well, we think about that, and we know that B is E over C. So the average force is going to be equal to Q over C average of VE. But the average VE, that's going to be rough. The average VE is going to be the RMS VE. So what that means is we could then say that we could then say that this average change of work here, the RMS, okay, we know that is equal to QVE RMS. So that's going to be, if we divide both sides by C, so 1 over C, 1 over C right here, then that's going to be basically the average force. Okay, now the average force is dP dt, where this is little p, that's momentum. So that means that the light is actually carrying momentum. So when light hits something, it actually pushes on it. It carries momentum. Conservation momentum even says if you have a flashlight and you turn it on, so you turn on a flashlight and the light comes out, it carries momentum this way. So conservation momentum, there's a recoil on the flashlight. Now you don't normally feel that. But the Navy has experimented with these ultra high-powered lasers designed to shoot down incoming missiles. They've explored these very high-powered lasers that would interfere with small boats that may be attacking. And one thing they discovered is these lasers do have enough recoil that as the laser light goes out one end, that the laser will actually scoot itself off the deck of the ship if it's not fastened down. Obviously to ships, so they rock anyway. It'd be silly not to have it fastened down anyway, but still there is a definite measured recoil there. And so this is a real effect. Light does push on things, and in fact that's a very interesting point, that light pushing on things comes out to relate in the area of astrophysics to the biggest that a star can be. The bigger the star is, the brighter it is. Once it reaches a certain brightness, it literally pushes its outer layers off into space. This is called the Eddington limit. And the Eddington limit determines the biggest and brightest that an object can be before the light actually pushes it away. I'll just use a term there, light pressure, because what we've got here is 1 over C, the rate of change here, okay, RMS equals the average force, okay, but force over area is pressure. Remember this, force over area is pressure. So that is pressure, and I'll make some kind of different looking P to indicate pressure, because we've got 3 P's now in this video. We got P for power, P for pressure, and P for momentum. Well, this is power, so 1 over C, power over area, this average power over area, equals the pressure. Well, average power over area, that's our pointing vector. So the pressure is going to equal to 1 over C times the pointing vector. And so now we have a derivation for the pressure. And remember, pointing vector, the magnitude of the pointing vector is the intensity of something. And so now this would be what you would get, for example, if you have absorption. So you've got an object right here, light is shining on it, and we say there's a pressure there, and the pressure is going to be equal to 1 over C times the pointing vector. Well, what if your object is reflective? The light bounces off. Well, think about it. Think back to physics 1. We know that force equals dP dt. Well, if the light's carrying momentum and it's being absorbed, The pressure comes from the transfer of the momentum from the light to the object. Here, if light reflects back, it's got the same momentum it did before, so the object has to get twice that momentum in order to have conservation momentum. So in the case of reflection, this is 2 over c times the Poynting vector. And so this would be an example of light pressure. And so next we'll do an example of that. So we'll actually do a numeric example next.